and squeeze it into a object of radius 3 kilometers, it would become a black hole. But this simple calculation would tell us. So, and then this value of R would correspond to something called as the Schwarzschild radius. And more generally, you talk about event horizon. So, you know, the event horizon is an imaginary surface and a unidirectional membrane where things can only go in and nothing can come out. Okay. So, from here we get an idea, and this is what I should have told this idea first and this idea later. So, here there is the event horizon. And nothing can enter, nothing can come out of it, right? So for a black hole, nothing can come out of the event horizon. So it's a unidirectional membrane. Things can go in, but nothing can come out. So now the point here was that the heavier the mass, gravitating mass, the deeper the singularity. So you see, we are trying to address some singularities. The most obvious singularity is if we run our universe backwards in time, we hit upon a singularity called as the Big Bang, right? This is another kind of singularity that we encounter for black holes. And even inside the black holes, you have the singularity. So we have been talking about our classical theory of gravity, classical field theory of gravity. We are able to construct. And how much is the limit for this classical field theory of gravity that explains to us is this is the limit. So it explains us all physics beautifully, wonderfully, large scale physics. But beyond event horizon, it breaks down. So classical field theory of gravity, which we call as general relativity, would break down beyond the event horizon limit. It cannot explain things further. And so this is, as at the beginning, our one of the main questions was need for a quantum theory of gravity. Need for this is, we are trying to address gradually what is the need for a quantum theory of gravity. Okay. So, you see what happens, even though general relativity is extremely predictive, very correct, but it has limitations. So, the just examples that I mentioned, like if you run the universe backwards in time, then you hit upon a singularity called as the Big Bang. And near that point, your general relativity would break down and you would need further some to explain things, understand things correctly, you would need a quantum theory of gravity. And you see, even black holes are also not eternal. They also eventually decay away. So, the radiation that comes out does not carry any information. So, it seems that the information as to what once made a black hole might be getting destroyed in the process. Okay? And then, but this will then clash with the unitarity of quantum mechanics. This would be inconsistent with the unitarity principles of quantum mechanics. So, this is one major point which more than 40 years ago led Stephen Hawking to say that no, we need to modify our laws of quantum physics in order to understand gravity. So if you want to understand gravity, you need to modify quantum laws. Now we know a little bit about, in our way, that is important for us, the classical field theory of gravity. And we gradually have also started coming to know, realizing what are the limitations, why we need a further quantum theory of gravity. So you see, if you go deeper into these singularities, your general relativity beyond event horizon would not explain the things. So we look for a quantum theory of gravity. Now, can we construct a quantum theory of gravity? Can we construct a quantum field theory of gravity in the usual way that we do in field theory or the conventional field theory? So, there is let me tell you again, we will have to go to for the main problem that we say is that the quantum field theory of gravity, if we construct it on par with the quantum field theory of other three forces, is not renormalizable. What does it mean? We have to understand this. We have to try to understand this. What does it mean? For the simplest example we can think of is QED. QED is the simplest example. So let us take QED as an example. So in QED there are four So these are 4 and 4, 8 diagrams. These are the lowest order or first order Feynman diagrams of QED theory, and they are the fundamental diagrams. For QED theory, you have 8 and only 8, no less, no more. Similarly, for other theories, you have certain fundamental first order diagrams, okay, for electroweak theory, for QCD theory. And if I would construct a quantum field theory of gravity, I would have similarly some fundamental vertices here. What is happening? Let us say an electron is going like this or like this, or so let us say a pair creation or a pair annihilation or scattering of an electron or scattering of a positron. So first few could be, you can think that with the emission of a photon, then you have 4, or with the absorption of a photon. So 4 and 4, 8. Okay? Pair creation, pair annihilation, electron scattering, positron scattering with the emission of a photon or with the absorption of a photon. So now you make all higher order diagrams in the QED theory, making use of the fundamental vertices of the theory, fundamental Feynman diagrams of the theory. So these are 8 diagrams in QED theory, and you can construct other diagrams out of this, and you can then calculate the transition amplitude or the transition probability for any occurrence of any theory. So for example, you consider, let us say, electron scattering, and so you see the diagrams that I made actually like this, it could also be, it means the same because they are topologically equivalent. Okay, so there is nothing in the angles and directions. This is just a line, and this is yet another line. To differentiate the two, a solid line is representing the fermions, and this baby line is representing the photon. Okay, so so basically you cut the two, then this is one vertex, this is another vertex, 3 vertices, and if you join the two, you get the so-called tree level diagram. This is the tree level diagram of the in QED theory for a electron scattering or a positron scattering. Okay. All right. And now I can consider another theory, another diagram. So this is Compton scattering. Electron and a photon. Okay. So this also, as you can see, if I cut it from here, this is one fundamental vertex. This is another fundamental vertex of QED, and I can construct this. So these are three level diagrams these are the tree level diagrams in the QED theory for a Compton scattering, for electron scattering. Now, in each one of the theories like QED, QCD, electroweak theory, there are some fundamental diagrams, lowest order radiative corrections. In a way, I am actually trying to recap in a nutshell, in a brief amount of time, but one teaches in advanced quantum field theory. Okay, but you take the example of QED because that is simpler to understand. So now there are these processes